Okay, we start now with the second part of the
Okay, thanks. Good morning, you guys. So, I think at the end of yesterday's lecture, I said some things in a somewhat unclear way, and I'm sorry about that. But the good news is that I got almost an hour and a half of sleep last night, so I think things will go much better today. So let me just summarize the things that we need to know from yesterday's lecture for today and for tomorrow and the next day. So we're studying the SYK model, this theory of n Majorana fermions. And let's imagine, so one quantity that we were discussing and that will be important to think about is the thermal partition function, z as a function of the inverse temperature beta. And you can write a formula for that in terms of a path integral over these n Majorana fermions with this SYK interaction, with the 4 fermion interaction. And we saw how, after doing a disorder average, so integrating over this these couplings J, we can instead study a collective field description of this model with these collective fields sigma and G with this action. And the important part here was that it was all proportional to n. So at large n, it was a semi-classical problem described by the saddle point and small fluctuations about it. And then where the trickier analysis in SYK gets involved is in analyzing this action at low temperature. And we didn't really establish much of this, but just told you what happens. And what happens is that low temperature, there's a special set of fluctuations in this G and sigma space that correspond to reparameterizations of time, like conformal transformations of the correlation function of the fermions, G. And that reparameterization is this field phi of tau. And it should be considered an element of diff S1 mod SL2R. And it's described by this action at low energies in the SYK model. It's called the Schwarzian action. There's a piece here which is the zero temperature entropy. This is independent of the field, e to the n times S naught. And then there's this Schwarzian action piece. This part of the theory describes the largest fluctuations in G and sigma at low temperatures. But so if you remember, I drew this picture of a valley, and this describes the integral. This describes the fluctuations in the direction of the valley. But there are also fluctuations perpendicular to the valley, and those are some other modes in G and sigma. We can write as G perp and sigma perp, and there's some action for those guys as well. We haven't discussed it very much. So this is the structure of the SYK model at low energies. Okay. So now, today we're going to discuss a different subject, although it's related. We're going to discuss the JT gravity, or Jakiv-Teitelbaum gravity. So to start, let's forget about SYK completely and just try to think of a way of describing a theory of two-dimensional gravity. In particular, we like a theory of two-dimensional gravity that has ADS2 as solutions, because we're going to try to interpret this in the context of ADS-CFT. Okay, so your first guess for a theory of two-dimensional gravity might be to try to imitate what we do in higher dimensions and write something like the Einstein-Hilbert term plus a boundary term but in 2 dimensions, this is problematic because the quantity in brackets is a topological invariant. It's proportional to the Euler characteristic. So if we vary this action with respect to the metric, then we find just 0. So, okay, in a sense, it has ADS2 as a solution, but it has any space as a solution. This theory is much too floppy. So this won't do. Now, what you can do to get a better theory of two-dimensional gravity, you can get of ADS2. You can get inspiration by thinking about cases in higher dimensional gravity where you have an approximately ADS2 geometry that emerges. So, for example, in 4 dimensions, if we study a nearly extremal charged black hole, nearly extremal Reisner-Nordstrom black hole, and we look at the near-horizon geometry, then we have a 4-dimensional geometry that looks approximately like ADS2 times S2. So we have an ADS2 factor, but we also have an S2 factor. And importantly, the size of the S2 is varying a little bit as a function of the position in ADS2. So in order to describe a better theory of ADS2 gravity, we have to remember this size. So there's one extra field that we'll have to include. So let me try to draw a picture of this configuration in higher dimensions. I'll draw a sketch of the spatial geometry of this near-extremal black hole. It looks something like this, where this region here is approximately ADS2 times some compact space. For example, ADS2 times S2, where what I've represented here, these circles are the S2. And this direction here is the radial direction in ADS2, and time is not shown. So the size of the S2 is approximately constant in the ADS2 region, but it's not exactly constant. So we can make up a field called the dilaton, and we can write that the area of the S2 divided by 16 pi g Newton is equal to a constant called phi 0. This is the area of the S2 in the extremal limit for the extremal black hole, plus a small correction, phi, where phi expresses the small correction of the area of the S2 beyond extremality. And this phi is varying a little bit as we move in this direction here. So if you reduce the higher dimensional gravity, keeping this field and the two-dimensional metric, then you get the action that we wrote here times phi naught plus another term So we imagine that we're expanding the higher dimensional action in powers of this small deviation phi from the extremal area. And the leading term will be this term here. That's proportional to just the extremal area. But this term is topological. So we need to go to next order to get a non-trivial theory. In next order, we have a term which is linear in this small parameter phi. And we have a bulk term where phi multiplies r plus 2. And then we have a boundary term. And instead of just writing the extrinsic curvature here, I've put k minus 1. You could have just written the extrinsic curvature. This theory here is called JT gravity, Jakob-Teitelbaum gravity. And it arises universally as a description of the near-horizon region of nearly extremal black holes, where they're developing this ADS2 factor. And we can use this as a starting point for a description of ADS2 gravity. Yeah?
Like the charged black hole is also gauge field in that case that I discussed.
Yeah, that's right. And so in order to get a good theory of two-dimensional gravity, we don't need to keep the gauge field. So we can just study this theory. This is enough. Okay.
Quick question before you go
Yeah.
on. There are purely classical spinner-based two-dimensional dimensions of gravity. That's not what we're talking about, correct?
This is purely two-dimensional gravity. So I'm not sure what you mean by spinner-based.
Well, basically there's a mapping where essentially you take the four components of, for example, a vector space-time vector, and you essentially map it on a 2x2 spinner, and so effectively you get a 2x2 or analog. So that's not what you're talking about, though.
No, no, no. Here the 2 is the dimension of the space-time. So
Right, okay.
right. So we're not studying 4-dimensional gravity anymore. We're studying 2-dimensional gravity. And your naive guess for a 2-dimensional gravity theory is topological, and it's not interesting. So we've had to include this subleading term proportional to the phi. So yeah.
Can you summarize that this action starting from Einstein-Hilbert action in 4 dimensions?
Yes.
And
Yes.
then S2 compactification.
Yes. Yes.
And that
You can also get it. You can also get it by looking at ADS3 gravity and taking and compactifying on the S1. So there, phi would be the size of the S1, and you get exactly this theory.
And then you switch off the gauge fields, and that's a consistent transition, something like that.
Well, that's a consistent theory. Yes.
No,
So
for
if
example,
we were describing an actual higher dimensional black hole, we would have additional fields. There would be a gauge field. There would be the KK spectrum and so on. But this is good enough for our purposes. This is the theory that will be related to a limit of the SYK model.
like,
Yes.
I'd like to make a comment.
Okay.
For example, one has magnetically charged black holes in ADS4, and the gauge field is turned on only in the theta phi directions, and then if one does a S2 reduction, then there will be no gauge field in the 2D theory, for instance.
Uh-huh.
Because the magnetic field will only be in the theta phi directions if one makes such a choice.
Yeah, but we'll also, well, okay. We can discuss this afterwards. Yeah. So this theory, the Joukiew-Teitelbaum theory, was discussed in the context of ADS-CFT, first by Almhiri and Polchinski. And, yes? We'll do that in a minute. So it's helpful to have an example of something to calculate in the context of ADS-CFT in mind. And a good thing to imagine calculating is the thermal partition function, z of beta. So this is a problem in Euclidean 2-dimensional gravity. And z of beta is a particular problem in 2-dimensional gravity with some boundary conditions that are related to beta. So those boundary conditions are as follows. First, we should study a 2-dimensional geometry with a boundary. And it should be such that the length of the boundary of our manifold is beta divided by a parameter epsilon. This is a holographic renormalization parameter, and we'll take it to 0 in a moment. So this is the length of the boundary. And the other boundary condition is that the dilaton phi should have some value. And we'll take it to be phi r, the renormalized value, divided by epsilon. So the ratio of these things is independent of epsilon. And but for the correct limiting procedure, we should take some small epsilon, impose these boundary conditions, and then we take epsilon to 0 at the end. Okay. So yeah. I guess I'll erase this board. So let's think about trying to compute this partition function. A very convenient procedure in analyzing this theory is what was suggested by a member of the audience a minute ago, which is to integrate out the dilaton in the first step in the functional integral. So the dilaton only enters in the bulk, multiplying this term here, and it enters linearly. And if we do the path integral over a contour where the integral is well defined, which would be a contour parallel to the imaginary axis, then the integral over phi just gives us a bunch of delta functions, a delta function at each point in space-time, setting r plus 2 equals 0. So if we integrate out the dilaton, we just remove the dilaton altogether, and we find the constraint that r should be equal to minus 2 everywhere in space-time. Now in 2 dimensions, this is a very strong constraint, because the scalar curvature completely determines the curvature tensor. And actually what this means is that we are looking at a piece of constant negatively curved space, so hyperbolic space. So this gives us a huge simplification of the path integral. We started by integrating over 2-dimensional metrics and the dilaton. the integral over the dilaton localizes the integral over the metric to just be over pieces of hyperbolic 2 space. So what's the type of piece of hyperbolic 2 space that contributes for our problem? So let me first draw the whole hyperbolic plane. So this is the hyperbolic plane, which we can write in some coordinates like this. So in these coordinates, theta is an angle, and rho is equal to infinity at the boundary, and rho is equal to 0 in the center. And an example of a configuration that would contribute to z of beta would be a region where we cut out some droplet from the hyperbolic plane like this, and we take everything inside that curve. The constraint on this curve from our boundary conditions that we discussed a second ago is that the length of the boundary should be beta over epsilon. And I've drawn it sort of at finite cutoff, but in the end we're going to take epsilon to 0. So this droplet will be very close to the mathematical boundary of the hyperbolic plane. Yeah?
This is the point where I get a bit confused, because if I start from canonical ADS-CFT, I would think what you need to do is to match the boundary radius 2 in the charged black hole to some UV ADS-4 region. There should be some matching procedure between these two geometries, and that should be the way one should do it. Now, I presume this gives you the same answer as that, but I don't quite see why.
Okay, so, well, the reason why we're not doing that is that we want a one-dimensional boundary. So we don't want to embed this in ADS-4. We want to just study the two-dimensional bulk theory.
So you could take the full ADS-4 geometry and just forget about all angular dependences. That gives you a full theory all the way up to the ADS-4 boundary, which is still two-dimensional.
But it's, well, it's not ADS-2 like near the boundary of ADS-4. So we want to describe something which is like ADS-2, just the ADS-2 part. And in ADS-4, where this mode would arise would be the ADS-4, there would be some transition between the ADS-4 region and the ADS-2 region.
Yeah.
And that would be at some fixed location. But the ADS-2 region would have some, basically some effective size. So the ADS-2 geometry that you would staple in there at the transition region would be this droplet. Where, and those would all be legal ADS-2 solutions that you can paste onto the asymptotically ADS-4. So the thing that we're putting as our boundary here would be the interface between the ADS-4 and the ADS-2 regions.
I understand that. I want to know why this is equivalent. It's not obvious to me.
Why what's equivalent?
Yeah, the description that you've given of a wavy boundary, why is that the same as just doing a more complete calculation where you actually do the matching?
Yeah, because in the more complete calculation, by more complete calculation, what you mean is a calculation where we're embedding this in a higher dimensional ADS space.
Yes.
And I would, well, whether we call that more complete or not is a matter of taste, I guess. But the reason why that prescription will give us this is that in that higher dimensional geometry, there will be some transition region between ADS-4 and ADS-2, and that's our boundary. And there will be an integral over modes in the metric that are relatively unsuppressed modes in the functional integral over the metrics. And those correspond to these droplets, the different shape of the droplet that you glue on to the fixed transition region between ADS-2 and ADS-4. A transition region will be some curve that has length beta over epsilon. And we'll glue in whatever ADS-2 droplet we like. So it will be exactly the same problem as we're studying here.
I believe that. I'm just trying to understand that.
I thought I'd explained it. I'm not sure how else to explain it. Yeah.
Similar to yesterday, when doing the dilaton integral, do we have to take some contours parallel to the imaginary axis?
Yes. Any other questions? Okay. So we have to do this integral over the shapes of these droplets. The only constraint here is that the length should be beta over epsilon, And you can draw many different wiggly curves in hyperbolic 2 space that have that length. One way to parameterize the integral over these wiggly boundaries would be to choose coordinates on the boundary here such that we parameterize the boundary length by a coordinate tau, such that the induced metric on the boundary, h tau tau, is 1 over epsilon squared. So that means that our tau coordinate runs from 0 to beta. So tau is measuring basically the rescaled proper length along the boundary. And we can give a parameterization of these droplets. It's a bit of a funny parameterization, but it's a legal one, by giving the coordinate theta as a function of that proper time tau. Sorry?
Are you allowing the boundary?
Actually, I don't need to specify that. In this limit epsilon goes to 0, they won't want to. So if we were trying to discuss the theory at finite epsilon, then we'd have to have that discussion. And the theory that sort of seems to be well-defined quantum mechanically is one where they do self-intersect, and that doesn't have a very obvious interpretation in terms of two-dimensional gravity. It would be nicer to have a quantum mechanical theory at finite epsilon where they don't self-intersect. But that subtlety isn't relevant in the limit we're taking where epsilon goes to 0.
So once I know theta of tau, rho as a function of theta on the boundary determinant.
Yes, yes, yes. Okay, so this would be one parameterization of the droplets. We should integrate over functions theta of tau. And now we need to understand the action for this integration variable theta of tau. So if we look at the JT action, this term is gone because r is equal to -2. This term here is a constant. This term is 4 pi. I think I should have put a minus sign here. The only term that remains is this term, involving the extrinsic curvature. And you can work out the extrinsic curvature. You can work out the extrinsic curvature for this boundary here as a function of the integration variable theta of tau. What you find is the extrinsic curvature is equal to 1 plus epsilon squared times the Schwarzian derivative of tangent theta over 2 with respect to tau plus higher orders in epsilon. So now let's take this expression and plug it in here. The 1 cancels this 1. We have an epsilon squared times tangent of theta over 2. The square root of h here gives us a factor of 1 over epsilon that cancels one of the factors of epsilon. Then the factor of the dilaton. Remember, at the boundary, we impose that the dilaton is equal to some renormalized value phi r divided by epsilon. So that epsilon cancels the second factor of epsilon here. So the whole action becomes four pi phi naught plus 2 times this renormalized value of the dilaton times the integral of the Schwarzian action. And this is the same action that we found in the SYK model, where this parameter theta should be identified with 2 pi over beta times the phi that we had in SYK. So this calculation justifies the relationship between the SYK model at low temperature and a theory of two-dimensional gravity.
What natural units are you working in? Because I'm used to curvature being having dimensions of twice inverse length. So
this thing here is in ADS units.
okay.
come from ADS4, you'd have also higher order terms in phi, but
Yes.
those are self-consistently small in this.
Yeah. Yeah. So, that's right. So if we were getting this theory by studying a higher dimensional near extremal black hole, then we would have some series of corrections in powers of phi. And the idea is that phi, the black hole will be close to extremal. So the area will be close to the extremal value. So phi will be small. So the expansion in phi, the phi squared term will be small relative to the phi term. And
Small here means 1 over n or 1 over
No, no.
J in SYK language?
Well,
Um,
actually, it's another parameter. It's just how close to extremality we are.
You think of it, temperature much smaller than the equivalent radius of the black hole. That's the parameter.
Yes, that's right. That's right.
So the bulk equations of motion will relate phi r as theta, and here so phi r will be identified by 1 upon g.
So the equations of motion for what will relate phi r?
The bulk equation of motion from dt gravity. So theta would get completely determined in terms of phi r. So phi r is your boundary condition.
Phi r is a constant.
Yeah,
So-
but I'm saying if I change phi r, at least on shell, there's the classical equations of motion in the bulk.
Yeah, that would be analogous to the equation that we get from varying the Schwarzian action with respect to theta. And that will give us our particular solution of theta, which is just theta equals constant. Theta equals tau.
Yeah, but then I'm saying that, so here we're writing it as a theta as a, we're going to do a path integral over theta.
Yes,
And
theta
phi r
is
completely not related to it at all.
That's right.
But I'm saying that the bulk equations of motion would relate those.
We're not imposing the bulk equations of motion. We're studying the full path integral. So it looked like we were imposing the equation of motion for phi, because the equation of motion for phi said that r plus 2 equals 0. And we restricted ourselves to constant negative curvature metrics. But that wasn't because we were imposing the equations of motion. It's because the full functional integral over phi imposes that delta function. So there's another equation of motion, the equation of motion for the metric. The equation of motion for the metric would indeed give us a particular solution for theta here. But that equation, the metric doesn't enter the action linearly. It enters it non-linearly. So that equation of motion doesn't become a delta function in the quantum mechanical theory. It becomes a saddle point equation, but it's not something that we impose on the functional integral. Yeah.
This might be related, but so if you include the quadratic term in phi, you'll also get contribution from geometries with positive curvature, right? So how do you think about that?
Yeah, so if you include the quadratic term in phi, then we're no longer able to restrict ourselves. Phi, the integral over phi no longer gives us a delta function. Instead, it gives us a sharply peaked Gaussian around r equals plus 2. So r equals minus 2. So this analysis will be a little bit corrected. In addition to having fluctuations in theta, we'll have fluctuations in the two-dimensional metric. And that's a much more complicated problem. So this limit, where this near extremal limit, where we keep only the linear term in phi, is a significantly simpler problem than that one. Okay. Okay, now I can erase this because, right, so what I was saying is that this gives us a relationship between the low energy limit of the SYK model, where the most important fluctuations are the fluctuations in this reparameterization field phi, and that's described by the Schwarzian action. We have the zero temperature entropy plus the Schwarzian action. And then we have an integral over these other modes. Now, in JT gravity, we have the same structure as the first part. We have this term here, which can be interpreted as the zero temperature entropy, and then we have the Schwarzian action. And in general, we could have fields propagating, in addition, fields propagating on the two-dimensional space, and those should be understood as somewhat similar to these terms, although not in detail. These terms don't correspond to any particularly natural set of matter fields propagating in ADS2. Yeah?
Can IR be dependent on tau?
Sorry?
Can we include boundary conditions such that phi r is a function of tau?
Yes, sure, you could do that.
Why phi not doing
So if you, right, so the question was whether you could choose boundary conditions where phi r is a function of tau instead of being a constant. And you can do that, but actually that's equivalent to this theory after making a reparameterization of the time. So it's not an essentially different theory. And in any case, the phi r equals constant is appropriate for getting the low energy limit of SYK. So this relation between the low energy action here and JT gravity basically explains many of the features that were noted that made the SYK theory resemble a two-dimensional black hole. And for example, this calculation would show that the SYK theory at low energies is maximally chaotic because two-dimensional black holes are maximally chaotic. But there are many other properties, and we're not going to discuss many of them. Yeah.
So you didn't say it, but I guess it's obvious from the formula is the relationship between phi r and n and j.
Yes.
So in higher dimensions, this phi r is something like m Planck, and if you kind of want it to be large in order for the theory to be semi-classical.
Yes.
Do you understand if there's a sense in in higher dimensions you can also define m Planck as sort of the scale at which gravitational scattering becomes strong?
Well, there's no dimension-full scale in two-dimensional gravity.
Well, phi r is dimension-full, right? In JT there is, right?
Yes.
Yeah, but this j is not a dimensionful parameter in the bulk theory. So in the bulk theory, the coupling constant is dimensionless.
Yeah, but that's like m Planck in ADS units, right? So I think the dimensionless version of phi r is like n in higher dimensional.
Yeah, it's well, sort of, yes.
So usually what we say is that if you kind of do scattering, right, at high, usually there's another way of thinking about m Planck is the scale where the sort of effective field theory of gravitational actions breaks down. But I was wondering if there's some version of that in 1+1 dimension. I thought about it a little before, and I couldn't think of a way to say that.
You're asking whether this theory becomes a bad approximation if we consider some high energy scattering problem in the bulk?
Like say including some matter, you have to include some matter or something, but yeah.
Including some matter, you mean in JT gravity or SYK?
Well, yeah, SYK is a UV complete theory, so I was thinking in, say, JT plus a few matter fields.
Well,
so there's some matter fields also.
No,
from SYK,
then
right?
nothing much happens here. The gravity is important in the high energy scattering and the matter fields are not. And that problem is completely well defined.
I mean, if you do a high energy scattering of
From the perspective of the bulk theory, JT gravity is perfectly UV complete.
Yeah, that's the
And
thing that's kind of
it
funny, 'cause some,
doesn't have any problem at high energies.
yeah, even though somehow this is like m Planck.
Well, I was trying to resist that interpretation. And
Yeah.
okay.
I wouldn't mind seeing these explicit analogies between phi r and n and j.
Okay. So okay. So as a next step, let's analyze the saddle point for this theory. So we've reduced the two-dimensional gravity theory to this fluctuating boundary, and we have an action for the fluctuating boundary. We're going to ask what is the saddle point for this action. And it won't surprise you to hear that the saddle point is just a circle. So an unwiggly circle, we have a configuration that looks like this. And that would be theta is equal to 2 pi over beta times tau. Now, this isn't a unique saddle point of this action or of JT gravity because we can take this circular droplet here and we can move it around in the hyperbolic space. Moving it around in the hyperbolic space, this is the gravity version of this SL2R redundancy of the description that we had in the Schwarzian theory. why we're integrating over diff S1 mod left quotient by SL2R. What that left quotient corresponds to is not integrating over the mode where we just move whatever shape we have here around within the ambient ADS2 space. So after fixing that redundancy in some way, this is the unique saddle point for this theory, just the circle. And actually, this circle corresponds to a two-dimensional black hole. And that might sound a little bit like overkill to describe a circle, or more precisely this disk here, as a two-dimensional black hole. But really what a black hole means, what a Euclidean black hole means, is a gravity solution where the time circle is contractible in the bulk. And the time circle here is this direction. It's running from 0 to beta, and it's clearly contractible in this space. But maybe to make it seem more obviously related to a black hole, we should study this solution in Lorentzian signature. So that's what we'll do next. And actually what we'll spend the rest of the lecture doing. So in Lorentzian signature, whoops. Okay. In Lorentzian signature, yes?
So you said that there's a, I mean, because the time circle is contractible, you conclude that there could be a black hole inside?
No. Not that there could be a black hole inside, but this is a Euclidean black hole. That's what a Euclidean black hole means.
But
It's
what
a
about this, for example, in ADS5 we have the thermal and graviton gas, and there couldn't be something equivalent like that?
right. The graviton gas, that's a configuration where the time circle is not contractible, and the ADS black hole is a configuration where this time circle is contractible, and that's the difference between them. Here, the time circle is contractible, and that's really what it means to be a Euclidean black hole.
How do you see this Schwartzian action that the time circle is contractible?
Well, from the Schwartzian action, you don't see the bulk at all, so you don't see that. I was making a statement about the interpretation of this thing in two-dimensional gravity, which is the interpretation of the Schwartzian theory in JT gravity. Okay, so in Lorentzian signature, instead of looking at a piece of hyperbolic 2 space, we're going to be looking at a piece of Lorentzian ADS2. So let me introduce that geometry. Here I've drawn the Penrose diagram for global ADS2. It's everything in between these lines here. And a convenient set of coordinates is the following. So these are coordinates where this boundary here corresponds to sigma equals minus infinity. The right boundary corresponds to sigma equals plus infinity. And the t coordinate is just increasing upwards like this. This capital T coordinate here is called global time for ADS2, and the full geometry here is referred to as global ADS2. And what this solution will look like in Lorentzian signature is some configuration for the boundary of a regularized boundary, a cutoff boundary, sitting inside this global ADS2 space. So we can understand what curve in the space that boundary is sitting on by taking our coordinates from the Euclidean ADS2 and continuing them to this picture here. So the continuation to real time of the coordinates that we had in Euclidean ADS looks like this: d rho squared minus sinh squared rho dt squared, where t is equal to I theta. And these coordinates do not cover the full global ADS2. These coordinates cover a region that's referred to as the Rindler patch of ADS2. So I'll draw that now. So surfaces of constant time, constant t time here, look like this. This is the surface at t equals 0. This is the surface at some positive time. This is t equals infinity. This is some surface at negative time. and this is t equals minus infinity. And surfaces of constant rho look like this. These are surfaces where rho is negative on this side of the diagram. And these are surfaces where rho is positive. Rho goes from minus infinity over here to plus infinity over here. Now, the configuration that we had as a saddle point of this Schwarzian theory for the boundary mode was just a circle. And a circle means a constant rho configuration. So the analytic continuation to real time of our circle in Euclidean ADS is a configuration where the boundaries are following this trajectory here. And from this perspective, it maybe is more clear that what we're describing here is a black hole. Because from the perspective of these boundaries, there are these horizons in the geometry. There's a horizon here and a horizon there. And actually, this looks a lot like the Penrose diagram for a maximally extended black hole in higher dimensions. Now, one sort of funny feature of this is that in Lorentzian signature, the boundaries have two disconnected components. Here the boundary curve was just one component, and over here we have these two disconnected components. So the interpretation, we need to understand how to interpret this solution, let's say in the context of the SYK model. So it's similar to the interpretation of the maximally extended black hole solution in higher dimensions. And it's actually just similar to the interpretation of the continuation to Lorentzian signature of the thermal state in quantum mechanics. So let's forget about gravity for a second and just think about quantum mechanics. We have the path integral that computes the partition function z of beta. That's some path integral which is on a circle in Euclidean time, a circle where the time runs from 0 to beta. And we can imagine cutting this path integral, let's say cutting it here at these 2 points, and erasing half of it. And now the path integral gives us a state. A state in the tensor product of two copies of the Hilbert space. That state is referred to as the thermal field double state. And it has the following expression. It's a sum over the energy eigenstates sum over the energy eigenstates of two copies of our quantum system called L and R for left and right. We sum over all the energies with this square root of the Boltzmann factor. So it's an entangled state of the two copies of our system, and it has the property that if you trace out one of the sides, you get the thermal density matrix for the other system. So that's what you get if you cut the Euclidean path integral that computes z of beta. If you take this state, what this geometry here describes is the evolution in real time of those two entangled systems. So the two boundaries should be understood in the SYK interpretation as two copies of the SYK model, a left copy and a right copy. And they're in an entangled state, this thermal field double state of the SYK model, and the JT gravity description of that is this geometry here. Okay, so we're now going to discuss a kind of interesting application of JT gravity. And the application is to understand traversable wormholes. And this is something that can be discussed in higher dimensions as well, but it's very simple to do it in 2 dimensions. The pictures are easier to draw and the equations are easier to solve. So that's what we're going to do now. So to start, let's notice the following feature of this geometry. So we'll think about it again as describing a pair of SYK models that are in an entangled state, but that are not interacting with each other. So they're evolving with their own separate Hamiltonian on the left and Hamiltonian on the right. Now, this is a description of this thermofield double state, but we can imagine making a small perturbation to it. Let's say by acting with one of the fermion operators on the right system at some time. In the JT gravity version, that would be like acting with some operator, let's say, at this time, on the right system, and it might create some perturbation that could propagate into the bulk. It can't propagate any faster than 45 degrees, but it could follow some trajectory sort of like this. And a notable feature of that is that this particle cannot propagate from the right boundary to the left boundary. That's a feature of this geometry. It's impossible to get from the right side to the left side, so you can't send, for example, a signal from the right boundary to the left boundary. And that's very reasonable because we said that the two quantum systems, two boundary quantum systems, were evolving under their separate Hamiltonians, h left plus h right, with no interaction between them. And in that circumstance, it's not possible to send a signal from one system to the other, even though they're entangled. This observation is one of the things that underlies this ER equals EPR discussion of Maldacena and Susskind. Okay. But one point about this is that the wormhole is, I'm referring to this as a wormhole. This is a conventional terminology for these, the maximally extended Schwarzschild solutions, where we have two asymptotic regions. These are referred to as wormholes or Einstein-Rosen bridges. The geometry that connects the left asymptotic region and the right asymptotic region is referred to as a wormhole. And this is a non-traversable wormhole, meaning that if you start in one asymptotic region, let's say on the right boundary, you can't get to the left one. But you almost can. In particular, if you start really, really early, at very early times here, then you end up very close to making it across to the left side, but not quite. Now, you could wonder whether this property is robust. Like, here we were just describing the propagation of the matter as on some trajectory in the bulk, but suppose we include the gravitational back reaction of that matter or of some other matter, is it possible to make the wormhole traversable? And it's not possible, and there's a general argument for that, but there's a sort of simplified version of the argument that we can make in JT gravity that's sort of interesting. So it's based on the fact that in JT gravity, gravitational back reaction is super easy to understand because the only dynamics that we have in the gravitational theory is the dynamics of these boundaries. So the metric in between is frozen to be ADS2, and the only gravitational degree of freedom that we have is the location of this boundary here and the location of that boundary there. Now, those boundaries are described by this extrinsic curvature action, or the Schwarzian action, which is a little bit unfamiliar. And there was an observation that was made by Kitaev and was discussed in a paper by Kitaev and Su that you can actually think about this action for the boundary particle as just describing a particle in an electric field. So the reason for that is as follows. If we take the action, extrinsic curvature, then we can rewrite this using the Gauss-Bonnet theorem as the following. This is just using the fact that the order characteristic of the disk is 4 pi. And in the JT gravity, r is always equal to -2. So we can replace this by the following expression. And this will be another legal expression for the extrinsic curvature action. But we can think about that as the integral over m of dA, where A is a gauge field corresponding to a constant electric field. And of course, we can write that as an integral dm of A. So the action that we got here is just the action that would describe the coupling of some particle to an electric field. And that explains these sort of funny trajectories here. The trajectories that we found here for the boundary particle are uniformly accelerated trajectories. And uniformly accelerated trajectories are what you get if you study a particle in a uniform electric field. So this particle has one side of the charge, this particle has the other side of the charge, so they're accelerating away from each other.
So we should think of the kinetic term as coming from the -1 reaction?
No, the kinetic term is coming, if you like, from the beta, well, it's simplest to describe this particle in an electric field if we think about it in the fixed energy instead of the fixed beta. And then we're integrating over the lengths with some beta term, and that gives a length term in the action. Yep.
So does the -1, but okay.
Well, that one cancels a divergence in this expression, and there's a small leftover which depends on this term.
Why is it okay to replace root G by GA?
Oh, so here we're taking a gauge field that corresponds to a uniform electric field, so it's proportional to the volume form. So the integral of square root of G would be the integral of dA. Yeah?
If there is an equivalent description of the constant electrical, as you say, there could be in principle Schwinger pair creation, and if there are infinitely many particles created, wouldn't that create some problem for back reaction?
Well, there could be Schwinger pair creation if we were studying quantum field theory, but here we're just studying two particles in this background. So that process doesn't exist. Although the solution that we're studying is similar to the solution that describes Schwinger pair production. Okay, so that means that the whole gravitational dynamics of these boundaries can be reduced to just studying a particle moving in ADS2 in an electric field. And that helps us to get a qualitative picture for what happens when we include the gravitational back reaction. So let's look at what's happening here. The particle is moving along. The boundary particle is moving along on some uniformly accelerated trajectory, and at some time t, it emits some particle with positive energy into the bulk. By conservation of momentum, the boundary particle should receive a small kick outwards. So the trajectory will look like this, where the old trajectory of the boundary particle was that. So it's sort of clear from this picture that what happens is the boundary particle gets pushed out closer to the actual boundary of ADS2, and that makes this wormhole less traversable. So the fact that we can only shoot positive energy into the bulk means that the boundary particle recoils outwards towards the boundary, and that makes the boundary particles closer to the mathematical boundary and makes the wormhole less traversable. So there's a connection between the fact that we have positive energies and non-traversability. And actually, this statement could be made into a precise statement using the positivity of the average null energy condition, average null energy operator. That implies the non-traversability of wormholes. And this is a good thing because this property should be robust, because we explained it by saying that just the fact that the two systems are decoupled from each other, non-interacting, means that we can't send a signal from one side to the other. So small effects from gravitational back reaction and so on won't change that, and they shouldn't make it possible to send a signal from one side to the other. Okay. However, what I want to tell you about now is an interesting development that started in a paper by Gao, Jafferis, and Wall, where they showed that there is a clever type of thing you can do in this setting that makes the wormhole traversable. And the idea of what you would like to do is clear. What we want to do to make the wormhole traversable is we want to pull the boundaries closer to each other. We can't do that by shooting matter in because that just recoils the boundaries outwards, but maybe there's something we can do to pull the boundaries closer together. So I'm going to state their setup first in the language of the quantum mechanics system that's dual to this gravity theory. So we're going to describe the modification of the evolution of that quantum mechanical system that will produce a traversable wormhole. So we take the Hamiltonian for the system, and to begin with, it was just the sum of the decoupled Hamiltonians for the left system and from the right system. And the fact that we had a sum of these two terms underlied the statement that we couldn't signal between them. But then we add a term which looks like the following. It's active only at time 0, and it involves it's a double trace coupling involving some operator on the left theory and a corresponding operator on the right theory. And actually, for somewhat technical reasons that I'm not going to get into, but that are important for making this work precisely, we need to assume that we're summing over a large number, large compared to 1, of these operators in setting up this interaction. So, yes, but I think you actually don't need to assume they're exactly the same for this to work. Okay.
I guess my question is, what's your criteria for establishing, like, when do we know, this wormhole is transversable?
Yeah, what it means that it's traversable is that you can send a signal from one boundary to the other. And that's a sharp criterion because it can be diagnosed by light rays.
Right, but what about because in the classical limit, that's just, a point in the middle where the tidal forces essentially diverge and there is no passing from one side to another. So I'm wondering, like, how do we establish in the quantum limit that is going to be different?
A quantum mechanical version of this statement would be that the commutator between operators on the left system and operators on the right system is 0. That means it's not traversable.
Right.
A non-zero commutator between operators in those two systems would mean that it's traversable.
Okay, so that's what we're looking for. Okay, fine.
Okay, so we've added this term involving operators on the left and the right. Now we're turning it on only at t equals 0, so we can think about this whole combined Hamiltonian as being the normal evolution, except that at t equals 0 we insert an operator that looks like e to the ig, o left or right, where I'm not going to write this sum structure, but you get the idea. So we act with this operator at time t equals 0, and then we continue on with the previous evolution. Now, what is the effect of adding this term to the Hamiltonian? We can think about this term here as a type of potential energy term. It's a potential energy term where the potential is minus the 2-point function of these operators. In the gravity theory, these operators are sitting at their respective boundaries at time t equals 0, on the left system and on the right system. And the 2-point function between these operators will be larger if the boundaries are closer together. Because of this minus sign, that means that the potential energy will be less if the boundaries are closer together. So adding this term to the Hamiltonian gives us a force which pushes the boundaries closer together. So this is precisely what we want in order to deliver a small impulse to the two boundaries. It's a small impulse because we're multiplying by delta of t, so it's acting only at one time. We can represent the effect of this term as the following. We start out with the original trajectory of the boundaries. They evolve to time t equals 0, and then there's something like a spring which acts briefly, pulling them together. And after that time, we find a new trajectory which looks something like this. The boundaries have been kicked towards each other a little bit, so their new trajectories will follow something like that. And now, as you can see, it will indeed be possible to send a signal from the right side to the left. Yeah.
You can have in a quantum theory, you can put G to be negative, I think, and so the quantum theories will interrupt, but still the wormholes will not be traversable.
Yeah, here I'm assuming that G is positive. That's the sign where the traversability happens.
But how it corresponds, how the correspondence works in the G negative term?
When G is negative, this doesn't help you traverse the wormhole. Yeah, it's sort of funny that it depends on the sign of G, but it's true. Yes?
Where do you see the boundary in this Hamiltonian?
So what I was describing here was the deformation to the boundary Hamiltonians. So this was in the description where we're describing the two quantum systems, one on the left boundary and one on the right. And when we translate that boundary, so the new thing that we're doing is adding this bilocal boundary interaction. So in the bulk theory, that corresponds to adding a term, which is just adding a term to the bulk Hamiltonian or bulk Lagrangian that corresponds to a product of bulk field operators near these two respective boundaries.
Can you make that more explicit? That translation?
Yeah, it's, well, this is just, that would just be the usual operator field dictionary in ADS-CFT. This operator O in the boundary would be related to the boundary limit of a bulk field. So we would need to be in a setting where the bulk of gravity theory contains some propagating matter fields. And there would be a matter field which is dual to the boundary operator O. We could call it phi sub O or something like that. And then this interaction term in the bulk would be described as phi sub O at rho goes to minus infinity times phi sub O at rho goes to plus infinity. Except it's not really rho equals minus and plus infinity. It's rho equals these points on the boundary. Yeah, that's right. So
it's different from a physical point of view. Somebody doing this is living in a different space.
Well, but we had already got it into the tensor product Hilbert space before when we were describing this picture. So this picture describes a state in the two entangled copies of the SYK model. So we've been working in the two copies Hilbert space for a little while. Yeah. Yeah. So in order for the the picture I drew here is a classical picture. What I drew was a classical geometry here where it's possible for a signal to propagate from the right to the left. And in order for that to be a good approximation, we need to satisfy a few conditions. One condition is that this parameter k needs to be large. And another condition is that the matter particle that's propagating through here can't be too high energy. Otherwise, it will interfere with the operation of this sort of traversabilification that we get due to these operators. So actually, it's a little bit subtle to understand the limit in which you get this classical picture, but there is a limit with large k and for a particular range of times where we send in this operator. The basic reason why there's a subtlety there is that if we send this operator in with too high of an energy, then it creates a kick to the boundary particle. The boundary particle will be kicked away, and now the interaction between the two boundaries, the O right, O left interaction, will be very small effect. It won't do much. So we need to avoid sending in particles that are so high energy that the back reaction associated to those particles makes the wormhole much bigger to begin with. That puts a restriction on what times you can send this particle in. Okay, yes?
The way you draw the picture, what happens to the geometry where this Rindler horizon intersects the boundary? Because this is something I don't understand from a geometric perspective.
What happens to the geometry when the Rindler horizon... So after we do this evolution, the horizon is now somewhere else. So the horizon would be here and here.
So there is a splitting between, so the wormhole is no longer a point. There's a splitting between the two intersection points.
I'm not sure what you mean. Yeah, that's true. There's no bifurcated horizon anymore. But, yeah. Okay, yes?
Why did it have to be a delta function interaction?
Yeah, it doesn't have to be a delta function interaction. Somehow it's... the reason why I wanted to stay with the delta function is that I want to have an interpretation of this as acting with an operator at some time. That's for an application that I'll discuss in a few moments. But it's very interesting to consider the case where the delta function is just removed altogether and we have a constant term. So we just add this term to the Hamiltonian. That case was studied... I had originally intended to discuss this, but I'm not going to have time. But that case was discussed in a recent paper by Maldacena and Chi. And building on work by Korkulu and Maldacena. And what they found was that leads to a geometry which is called an eternal traversable wormhole, where it's not just that the boundaries have some kick and you get a brief period of traversability. So if delta of t is replaced by 1, then what you get is you can get a configuration that looks like this, where the boundaries are static. So they have some tendency to accelerate away from each other, but that can be compensated by a constant sort of spring holding them together, and you can arrange to have a static configuration like this. So that gives a representation of global ADS2 rather than Rindler ADS2. This is like a wormhole where you can go from one side to the other and then back again and so on many times. So it's interesting to consider that case, but we're not going to do it in the rest of the talk today. Yeah?
So this interaction already occurs with the boundary, so it seems to me that the boundary is already communicating.
Yeah. Okay, great. So this is the next comment I was going to make. So I wanted to make a few comments about this. So the first one is what happened to our argument that you can't send signals from one side to the other because the two theories are non-interacting. Well, here they are explicitly interacting. The left and the right systems are interacting with this term, so it's possible to send signals from the right to the left, and indeed that's what we found. Now, you might think that makes this seem rather trivial, because, okay, maybe we shouldn't congratulate ourselves too much on discovering that you can send signals from the right side to the left side when we introduced into the Hamiltonian a term that does exactly that. Like this term can annihilate some particle on the right side and create a corresponding particle on the left side. So we shouldn't be too proud of our accomplishment. However, that's not true. Well, it is true, but it's sort of irrelevant. One way to see why it's irrelevant is the following. Let's imagine that in the bulk we had two different types of fields. We had fields related to these O operators, and then we have some other fields. Let's call them chi. And the O and the chi fields, let's say that they're not interacting except through gravity. And what we're going to do is we're going to add to the Hamiltonian this term involving only the O fields, but not the chi fields. So what that means is that if you're an O quantum, particle in the O field, then indeed you can sort of be annihilated on one boundary and created on the other boundary. Annihilated on one boundary here and created on the other boundary here. So that gives a way for you to get from one side to the other if you're an O quantum. But if you're a chi quantum, it doesn't. It doesn't seem to obviously help you get from one side to the other at all. However, this works for the chi particles as well as the O particles. So it's not simply that there's some stupid thing happening where you're going to the boundary and getting annihilated and created on the other side. To put it another way, we can already see that isn't happening because we have a picture of what's happening in the bulk. And what's happening in the bulk is the particle is propagating through the wormhole. It's not that the particle is coming out here and then like jumping through this O-O interaction, at least not in an obvious way. So that's the sense in which this is non-trivial. That the traversability happens not in the obvious way you would think, sort of through the UV, but through the IR, through the wormhole. So, yes? Yes, that's right. The average null energy condition is violated in this case. This coupling induces some negative energy. And that's possible because the average null energy condition is only supposed to hold in cases where the geodesic is achronal. And this is a case where the geodesic would be chronal. So the average null energy condition is not supposed to hold in this case, and indeed it doesn't. Yes? Simultaneous what? Oh, yes. Yes. Yeah, it's quite weird. But from the perspective of the bulk theory, it's quite weird. But from the perspective of a quantum mechanical description of this gravity theory, where we have two quantum systems that are in an entangled state but not interacting with each other, makes perfect sense. We can imagine that we have two SYK models in the lab, and they're interacting with each other, and we can just take a wire or something that couples them together briefly. And that would induce this type of interaction. No. The SYK models don't have to be far away from each other. They're far away from each other in the dual geometry that describes those models. But they could be just sitting on two. I don't know what material you need to give the SYK model, but two of those, and they're just sitting in the lab, and they're close to each other, and there's some time scale associated to the aerodynamics, and on a much faster time scale than that, you can make them interact. You can pull one out and put in the other one, and so on. So this type of thing sounds pretty crazy from the perspective of gravity, but we know that it makes sense from the perspective of ADS-CFT. Yes.
You have negative energy. The energy is still bounded below here.
Yes. It's a small amount of negative energy. Yes?
We had an entangled state, and Hamilton is also coupled. So would it also work if I start with some unentangled state? So this too is...
No, and I'll comment on that in a second. It won't work in that case.
Is there any causality argument which would tell you that it can't go through the UV and it has to go through the IR? Or is that a discovery?
Yeah, that's sort of the non-trivial point of this gauge-Jeffers wall thing. That was the thing that was really surprising about it, is that it happens through the IR. And yeah. Okay, so there's one other comment I want to make before we move on to the next application of this, which this one is going to be important for what we discuss next, but it's kind of hard to grasp for some reason the first time, so please bear with me. Let's go back to this picture. What we were describing in this picture was the two entangled but non-interacting systems evolving here. Then we gave them a kick by turning on this interaction term. And then we turned the interaction term off again, and the boundaries went back to doing their own thing, but they had received a kick. So let's imagine that we're studying the boundaries at some later time up here. And now let's evolve that system backwards in time using the original unperturbed sum of the Hamiltonians. So if we evolved it backwards in time, including this interaction, then we would just reverse our steps and end up here. But let's evolve it backwards in time without this interaction. So just backwards using h left plus h right. So the ordinary decoupled evolution. Then no spring occurs at time t equals 0. And the trajectory of the boundaries will follow this trajectory like this. They'll look like just uniformly accelerated trajectories, and they will not agree with the previous ones there.
So those I'm confused. What's the direction of time on the left?
Well, here we're evolving forwards. So I'm considering a notion of time where both systems are evolving forwards this way.
That's not the notion you had before.
It is. That's this Hamiltonian total is h left plus h right. It's not h left minus h right. So there's a notion of time evolution which annihilates the thermal field double state, where we evolve forwards on one and backwards on the other. That's not the one we're using. We're evolving forwards basically in global time. Okay, so thought of from this perspective, there are these two different uniformly accelerated trajectories of the boundaries. And the acting with the spring switches us from one set to the other set. Okay, that's going to be important in discussing the next thing. So the next thing I want to do is use this traversable wormhole setup to give an example of a protocol for accomplishing a quantum information task that's known as the Hayden-Preskel problem. And this is a problem which is related to extracting information from an evaporating black hole. And it's based on the following. So let me draw a quantum circuit diagram for an evaporating black hole. So here's our black hole. We have some input in some state and some output. And let's imagine, as a part of the setup of this Hayden-Preskel story, that the black hole is not in a particular pure state at the initial time, but instead it's in a maximally entangled state with some quantum computer. So this is our setup. We have a black hole, and it's maximally entangled with some quantum computer. Now, the Hayden-Preskel story is based on the following thought experiment. Let's imagine that Alice over here sends some message qubit in some state, into the black hole. And somebody over here with this quantum computer monitoring the black hole and monitoring its Hawking radiation wants to try to read the message. Well, the rather remarkable result of Hayden and Preskill is that all they need to do is basically they don't need to collect a bunch of Hawking radiation from this evaporating black hole. They just need to collect basically 1 or 2 qubits of Hawking radiation. And they can add that to the previous system, which is maximally entangled with the black hole. They can do some complicated operation on their quantum computer, and they will get Alice's message. Now, this led to a type of funny paradox. Well, so the paradox is based on the following. I'm going to draw a Penrose diagram for a black hole, let's say in flat space. Maybe this one is more familiar. So outside the black hole over here, we have the quantum computer. And it has a bunch of particles that are maximally entangled with the black hole. And at some time here, Alice sends in her message. Now, the person operating this quantum computer collects a couple of bits of Hawking radiation, adds it to their previous stock of particles entangled with the black hole, and they can do some complicated operation at this time, and out pops Alice's message. Now, the paradox is that they can take that message and they can, let's say, jump into the black hole with it. And we can imagine that Alice's message to begin with was accompanied by some kind of a rocket, which, after it fell into the black hole, sent it up this way. So at this point here, we'll have 2 copies of Alice's message. We will have cloned this quantum state. And this is impossible in quantum mechanics. So this leads to a paradox with the idea that you can easily extract Alice's message before the black hole has evaporated.
Quantum computer is only monitoring just a little bit of the Hawking radiation, not keeping track of all of it.
Well, it has to keep track of a huge amount of stuff to begin with. And then it just needs 2 more bits. And you do some operation and you get Alice's bit. You get Alice's message. Okay.
Independent of how complex Alice's message.
Well, that's if Alice's message was 1 qubit. If Alice's message is k qubits, then you need to get of order k bits of Hawking radiation. Or if you're only able to measure classical aspects of the Hawking radiation, you need 2k. Okay, so now, what does this have to do with the traversable wormhole discussion? So we're going to think of the traversable wormhole as a version of this process. So our geometry had 2 entangled quantum systems, which represented a black hole with a wormhole connecting the 2 asymptotic regions. We're going to think of one of those quantum systems as the physical black hole. So here's our setup. I've drawn this picture many times, and actually I drew it 4 more times hidden behind that blackboard. So you'll see that in a second. So here's our geometry, and we're going to interpret the one on the right as the physical black hole. And we're going to interpret the one on the left, which is entangled with it, as the quantum computer in the Hayden-Preskill setup. Now, if you're uncomfortable thinking about the black hole as a quantum computer, you can think about the following. We could think that the quantum computer either is simulating the black hole, or that the person operating the quantum computer has decided to collapse all of the information into a black hole. And that's their way of doing the quantum computation. It doesn't sound like a very good idea, but actually it will work. So now Alice sends a message into her black hole. So here's the message. It doesn't propagate to the quantum computer. However, what we can do is we can use 1 qubit from the right side. That's analogous to grabbing 1 qubit of the Hawking radiation. And we can act with that qubit and the left system in some way to activate this spring, which kicks the left boundary onto this trajectory, and now the qubit propagates to the quantum computer. So in this way, Alice's message becomes registered in the quantum computer. It becomes part of this left quantum system. And this sounds almost ridiculously naive because, I mean, what we should be doing here somehow is like analyzing a quantum algorithm to show that we actually got the message on the left side. But as gravitational physicists, the way that we study quantum algorithms is that we solve Einstein's equations, we solve bulk gravity equations, and the validity, the success of the algorithm is just the fact that this particle has propagated to the left side. It's physically propagated to the left side where our quantum computer is. So this is a sort of weird way of analyzing computer science algorithms, but it's a legitimate one.
So don't you need your kick to be classical for this picture to make sense?
So that's right. So in order for this to work very cleanly, we'll have to use not just one bit from the right side, but k bits, where k is significantly bigger than 1.
Have to be of order n or something.
Oh yeah, it doesn't need to be of order n. If k is large compared to 1, then it will be classical up to corrections that are of order 1 over k. So we'll get 1 over k, so the classical picture will be correct to approximation 1 over k. So
Why isn't the back reaction in some sense of order 1 over n?
well,
Back reaction of your kick times the
But
gravity.
you want to
The
send
ba-
the photons, you don't want to send Douglas.
the back reaction is of order 1 over n, but if we send this particle early, then we only need a very small opening of the wormhole to fit through. So basically what happens is we send this particle early at a time which is logarithm of n. And that allows the particle to pass through an opening which is of size 1 over n.
So what's the analogy?
Okay, one more question, and then I'm going to finish because I'm getting short on time.
What's the analogy of the spring in this case?
In this case?
Yeah.
Yeah, the spring is somehow part of what's happening inside this complicated quantum computation that you do, including the new Hawking radiation and the old Hawking radiation. So the complicated quantum computation that you do in this case is you act with O left, O right, and then you just wait, and the particle emerges in the memory of the quantum computer. So it's actually a very easy algorithm. So, okay. Now, what we're going to do now is try to understand what happens with this paradox. And I have a bunch of pictures to show trying to set up this paradox and show how it's resolved when we think about the Hayden-Preskel protocol as being implemented by this traversable wormhole. So, okay, so we're going to go through these pictures one at a time, from left to right. So first, let's set up the analog in our two-dimensional black hole of this paradox here. So we start with the black hole over here. Alice throws her message in. Her message is accompanied by a small rocket booster. It falls into the black hole, and some time after passing the horizon, the rocket activates, and it shoots Alice's message up this way, but the previous container of the message continues propagating in this direction. Something has to continue propagating in this direction by momentum conservation. But Alice's message itself propagates up here. And now we're in danger, if we're able to somehow reconstruct the message and jump in, we're in danger of having 2 copies of the message. So that was the setup to this paradox here. So now let's see what we have to do in the quantum computer to recover the message and see how it avoids cloning. So here's the first step in the procedure. The procedure will be more complicated in this case than it was in the previous case because of the rocket booster. But the first step in the procedure is the same. We start at early times, and at t equals 0, we activate this O left, O right interaction that creates this spring which pulls the trajectories slightly closer to each other. They get slightly closer to each other, and now Alice's message doesn't make it to the left boundary because it was shot off in the right direction. But the sort of empty container that previously contained her message does propagate to the left boundary. So the operator of the quantum computer on the left side discovers at this time, aha, this empty container of a message has arrived in the memory of my quantum computer. They're disappointed by that, but they don't give up completely. So what they do is they extract the empty container. So they remove it or move it somewhere else in the memory of their quantum computer. What that means in the geometry is that they absorb this particle. So they absorb the particle, and then they take their quantum computer and they run it backwards in time. And they're going to run it backwards in time without adding the spring interaction. So they run their quantum computer backwards in time, but first they removed that rocket ship empty container. Now they're evolving it backwards in time like this, but the particle that was formerly here is no longer present in the geometry because they removed it. With this particle no longer present, Alice's message is on a trajectory backwards in time that doesn't sort of get recombined with some rocket booster that travels back out to the right boundary. Instead, it propagates downwards to the left. It continues on its trajectory. It continues on its trajectory until it hits the left boundary. So our clever operator of the quantum computer on the left side has initially been disappointed, but they reacted in a very reasonable way, and they evolved their computer backwards in time, and now they have Alice's message. They have Alice's message in the memory of their computer, and they do the same thing that they did with the empty message container. They move it somewhere else in memory, which means that they remove it from the geometry.
Do they also have to run the right side backward in time?
No, they don't have to run the right side backward in time.
The message will come back.
Yes. So one way of seeing what's happened here is let's look at the left and right systems here and evolve them forwards and backwards without the spring, without the left-right interaction. Then at this point, the right boundary will follow this trajectory. The left boundary will follow this trajectory. So at this time already, what's happened is Alice's message here is no longer part of the right system. It's part of the left system. So evolving the system on the left forwards and backwards is enough to recover Alice's message. So the operator of the quantum computer on the left evolves to early times, extracts Alice's message, so it's no longer propagating into the bulk. And then, okay, now this earlier point about realizing these two systems in the lab becomes relevant. We're supposed to imagine that this quantum computer, although it represents a black hole, is something which is sort of in the same space as the original observer of the black hole. So this whole left system, we could imagine, was this quantum system here. Its dual description was a geometry with two asymptotic regions, but the left quantum system is just some object which we have outside the black hole. So the operator of the quantum computer is actually living outside the right black hole. They have a copy of Alice's message, so they can take that copy of Alice's message and jump into the black hole with it. That's the situation that was very dangerous here, because they were falling into the black hole with one copy of Alice's message, and they were going to meet a second copy behind the horizon. But the second copy is no longer there. So the resolution of this cloning paradox is that the somewhat complicated operation that you have to do to recover Alice's message from the black hole removes it from the region behind the horizon. That sounds impossible, because operations that you're doing outside the black hole, how can they possibly affect something, remove something from the region behind the horizon? And the reason it's possible is that the quantum computer that you have that's entangled with the black hole is connected to the black hole through another geometrical connection. It's connected through the wormhole. It's not just connected through the obvious connection in space between the quantum computer and the spatial and space-time geometry. It's connected in some non-trivial way through an emergent wormhole that connects these entangled systems. And that geometry, that's sort of a back door to the interior of the black hole that it's exploited by this algorithm to remove the message. So this is a very special case of the Hayden-Preskel protocol, where we use these thermofield double states of two black holes. And it's an open question whether something like this could help resolve this problem for actual real evaporating black holes, which don't form thermofield double states with their Hawking radiation. But it's at least possible that, at least suggests that a more complete analysis of that problem might remove the paradox. Okay, I'm out of time, so thanks.
One small question. So when the removal was done, was the message behind the horizon, or did the horizon shift so that the message could be retrieved from a path which was not behind the horizon?
It's behind the horizon. It's behind the horizon, and it becomes accessible to the other boundary. So it comes outside the horizon of the other system. So the message is, it's behind the horizon of the...
It was outside the horizon.
Yes, it became outside the horizon after acting with this spring operator. Yep.
In the last diagram, why is it necessary to remove the timeline?
Remove this one?
Yeah.
Well, okay, let's imagine that our quantum computer operator doesn't remove it. Then it's here, but they don't have it. So when they move over to the right side, they can't jump in with it. So in that case, the message is here, and if they jump in, they find it. But they don't have a second copy themselves, so there's no paradox.
Just to get their own copy, they have to remove that one. To get their own copy, they have to remove this one.
Yes, yes, yes. And that's just, one way to understand that is just the ordinary no-cloning property of ordinary quantum mechanics. That if you have recovered this message here, that you've removed it from its original, yeah.
You said that in the Hidden-Pascal protocol, the quantum computer has to be maximally entangled with the black hole.
Yes.
One sort of obvious way is to wait until the page time and collect all the outgoing Hawking quanta. Is there some other way to achieve such a quantum computer?
Well, a relative of this question is whether it's possible to make black holes in thermal field double states. So whether you can create black holes that are in some state where it's maximally entangled with another black hole. And actually, this one candidate procedure for producing black holes in that type of state is to use this O left, O right interaction. So you set up this Hamiltonian that was discussed by Maldacena and Xi. And if you look at the ground state of that Hamiltonian, it's similar to the thermal field double state of two black holes. So that might be a way of creating thermal field double states of black holes. But an important point, which I would like to re-emphasize, is that in the case that you described, where the black hole becomes entangled with the quantum computer because the quantum computer has absorbed the first half of the Hawking radiation, the joint state of the black hole and the first half of the Hawking radiation, in that case, will not be the thermal field double state. And it is not obvious how to use this protocol in that case. In fact, there's a paper by Harlow and Hayden where basically what they argue is that it's extremely difficult to take that state and act just on the quantum computer to turn it into the thermal field double state. So there's a sense in which it would be very difficult to use this protocol to actually extract information from the black hole, but it might be that it's the easiest way of doing it.
So did Hayden and Pascal assume that there was something like this operation that they do to retrieve the information from the few number of bits? Does it act on the black hole as well? Like this O left, O right?
Yeah. Let me clarify that. Their operation acts only on the quantum computer. But it acts on the quantum computer after it's absorbed a couple of bits of Hawking radiation. So in order to make the analogy to our problem, we regard the bits that O left acts on, that O right acts on, as being the bits that we get access to by the Hawking radiation process. And those now should be considered part of the left system, and we're allowed to do combined operations on the left system and those bits. So the simple interaction O left, O right is an example of such an interaction.
Any further questions? Okay, so let's thank Douglas again.